All right, you've made it. Now's the time you've been waiting for. Examples. All right. The key place to look, if you're looking for more examples than what we're talking about here, are 2D examples are located in section 9.1. 3D examples are in section 10.7. We are going to be, I've consolidated those two ideas because it's the same idea. They're all both vector functions. All right, so let's start out with an example that looks like this. R of t is equal to t squared minus 2t, comma, t plus 1. All right, we're going to do, let me clean this up a little bit, t squared minus 2t and t plus 1. We're going to do this in 3 different ways because it's good to think of this in a couple of different ways. We're going to graph it by hand. Right, when you were learning how to graph regular functions, you did that by hand. Then we are going to graph component-wise and combine. And then we're going to graph in a computer. All right, all of these have pros and cons. And they each give you a different feel for how these functions work. So that's why we're going to do all of them, at least for this example. As we keep going, we'll do more and more in the computer because that's why we have a tool. We have a tool for having a computer. All right, so when one thing was missing from this definition, and that was a domain. What's the domain of T? All right, so we can either use the domain, just like we talked about last time, which was we look at each of these functions and we decide each of the component functions, and we look at what the domain of those are. Well, in both of these two examples, they're polynomials, and polynomials have the domain all real numbers. So let's just keep that domain for now. The domain of T is all real numbers. Okay, and let's graph it by hand. All right, so to graph by hand, let's plot some points. All right, so we're going to plot. Remember, now we have a T. Why don't we write this down? So this is, let's choose some colors here. We've got this one, we've got this one, and then let's use those colors. And we're going to say, so this is x of t is equal to t squared minus 2t, and y of t is equal to t plus 1. And so what we need to do is we need to graph t. We need then x of t, and we need y of t. Oops, I wanted to use that color here. All right, y of t. All right, so we're going to plug in different values of t. Let me just use some black for now. If t is equal to -1, t is equal to 0, t equals 1, t equals 2. So if t is equal to -1, what do we get? So plug in -1 into x of t. So -1 minus 2, -1, that's 3. plug in 0. 0 minus 0 is 0. Plug in 1. 1 minus 2 is negative 1. Plug in 2. 4 minus 4 is 0. Let's go one more down. And plug in 3. 9 minus 2 times 3 is 9 minus 6 is 3. So those are the x values of this function. Now let's do the y values of this function. So the y values, we plug in t into t plus 1. So negative 1 into t plus 1 gives us 0. 0 into t plus 1 gives us 1. 1 into t plus 1 gives us 2. 2 into t plus 1 gives us 3, and 3 gives 4. Okay, so those are our points. We now, you know what, look at me, I have a chart here. I already have a grid, so don't just draw a random grid there, Chris. Okay, so let's break this down a little bit so that we can see a little bit better. Actually, here's what I'm really going to do. Let me start over. I'm going to expand the size of this, and then I can put everything in here. Up, up. So t equals negative 1. We get 3 comma 0. So this is 3 comma 0, and this is at t is equal to negative 1. And then 0 comma 1. This is 0 comma 1, and this is t is equal to 0. And then plug in t equals 1. We get negative 1 comma 2. So this is negative 1 comma 2, and that's at t equals 1. And then t equals 2, 0, 3. And then the last point that we have plotted here is going to be at 3 comma 4. And that's when t is equal to 3. So if we now connect these, we can see this path that is traced out by this curve. Right? Remember, this isn't the graph of a function. This is the graph of the range of the parametric function, which is just this curve, this parametric curve. Okay, and it has a direction, right? So this curve has a direction. So you follow along the curve, and the curve might actually intersect itself. It might come back over itself. There's lots of different things that might happen. But remember, this is a one-dimensional thing. It's not like it splits somewhere. It follows this curve along the way. While we're here, let's talk about what if the domain is not all real numbers. What if the domain, so consider this function. So the function we had before was t squared minus 2t, comma t plus 1. But on the domain, t goes from 0 to 4. All right, because before, when the domain was all real numbers, this curve extended out off to infinity that way. So came from negative infinity this way, extended off to positive infinity that way. So if we restrict the domain, maybe we'll use a different color here just so that we can keep track of it. If we restrict the domain, then this function before 0 doesn't exist. The function starts here. This is the initial point. And this is what? This is r of 0. And then we need one more point on here. When t is equal to 4, we get 16 minus 8 is 16 minus 8 is 8. And t is 4, that's 5. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is our 0.85. And the range, so the parametric curve, starts at the initial point and ends at the terminal point. Okay, and so this is R of 4. Right, and so if you're looking to figure out what the initial point is or the terminal point is of a of a parametric curve, you want to plug in what the boundary value is. See, this was t is 0, t is 4, we plug them in, and that gives us the initial point and the terminal point. All right. So that was one way. That was graphing, just plotting points. And that's how we all learned how to graph anyway, early on. Now let's use a little bit more of our personal history, a little bit more of our understanding, and use it to graph this parametric function in a different way. And so what we're going to do is this version right here, graphing component-wise and combine. So what I want to do is I want to take these two equations, graph both of those, and use those to combine to create the parametric equation, the parametric curve. All right, so let's move down here. We're all up in those colors right here. All right, so let's graph component-wise and combine. I think this color's not dark enough. All right, so we're going to graph component-wise and combine. So here's what we're going to do. We had two equations. We had x of t was equal to t squared minus 2t. And we had y of t was equal to t plus 1. Now we know what these two functions look like. So t squared minus 2t, this is t times t minus 2. So that means it has a 0 at 0 and at 2. It's a parabola pointing upward that has a 0 there and there. Whereas t plus 1 is a function that looks like this. All right, and so now what we want to do is we want to combine these two things. This is the x-coordinate, and this is the y-coordinate. So what we need to do is we need to look at this, and if we're going to graph these things, then what we need to do is we need to keep track of what the x-coordinate is and the y-coordinate is for the same value of time. So here we have time equals 0, and this is time equals 0. So from time t equals 0 to time t equals 2, the x value started at 0 and goes to 0. So this is x equals 0, and this is x equals 1. And here y, as y goes from 0, as time goes from 0 to 2, the y value goes from 1 to 3. So that's going to tell us that our curve does this. Because, so what we're doing is we're looking at this x curve, and we're looking at this y curve, and we're putting them together. And we're saying from 0 to 2, this is t equals 0, this is t equals 2. From 0 to 2, the x value decreases down to -1 and increases up to 0 again. So it goes from 0 down to -1 up to 0. So that's what the x value has to do. It has to start out at 0 and go up down to -1 up to 0. Similarly here, the y value, it starts off at 1 and goes up to 3. So as the x value goes from 0 to -1 back to 0, then the y value has to go from 1 to 3. And so that's giving us this curve. It takes some practice to see that. We'll do another example shortly where we're going to have to keep in mind two functions at the same time. But this is another way to graph the parametric curve x of t comma y of t. All right, and then you would extend that by looking at the curve, of course. Okay, and the last thing we want to do is actually use a computer. And I mean, it's always good to know how to use a computer to do these things. All right, so let's go over to our screen here. And I'm making this notebook available to you on our course webpage. So what we'd like to do is we'd like to plot our function. So when you're using Mathematica or Wolfram Alpha to plot a parametric equation or a vector function, you use the function called parametric plot. And so what parametric plot does, in order to do this, you need to specify what the x function is, what the y function is, and what the range of the variable is. I mean, I guess this is the domain of the variable t. I'm using -10 to 10 to approximate -infinity to infinity. I could have chosen t goes from -100 to +100, but -10 to 10 was enough to get out of the picture anyway, out of the window that I defined by using plot range. So here I'm specifying here that the x values go from -10 to 10, and the y values go from -10 to 10. So all those things together, when you evaluate that, that gives you the picture here of the curve, that was the same curve that we drew before. Let's say we wanted to restrict the domain. If we wanted to restrict the domain, you can just plug in the values of t that you want to restrict it to. Here, I'm restricting t goes from 0 to 4. All right, and let's say we want to use the capabilities of Mathematica to maybe add in some motion to just watch the piece move. So here I'm using something called the manipulate function. This is the manipulate function that allows me to move some points. Here I'm moving the red point from when t is equal to 0 to 4. So this is just a good way to see that the point starts off at the bottom and goes up along the curve. It also tells me what the initial value of the function is, 0, 1, and the terminal value of the function on that short domain. All right, so we went through 3 different ways to graph the same function. I'm going to stop here, and the next video will be full of many more examples. See you shortly.